Hello everyone, today I'm going to explain Lagrange multipliers and the construction of Lagrangian. I will try to make my explanation very intuitive because I think to have an intuitive understanding of what's going on is really important in order to not forget. So what is it? Lagrange multipliers starts with an optimization problem, either a minimization or maximization, and we have constraint. So we don't need to have one constraint, but for the sake of simplicity, in this video, I will go with one constraint. Then in the next videos, I will also explain how we construct our Lagrangian when we have multiple constraints. So first things first, we start with a problem, an optimization problem. Let's say we have a function of x and y and then we have a constraint. As you can see, this constraint is basically a circle centered around 0. So we have a function that we are trying to maximize, and we have a constraint that is a circle. So what it's basically saying that what are the values of x and y that will maximize our function fxi, but at the same time it will be on this circle. And the proposition is that at the optimal points, the gradient of f is equal to lambda gradient of g. Why do we have lambda here? Because we don't care about the direction of the gradient vector, we only care about the direction. So it says that at optimal points, the gradient of f is equal to the gradient of g. The directions, they are the same. So what happens here? In order to visualize it, we should first understand how these functions look like and what kind of surfaces they form in the space. As you can see that our function f, if we try to visualize the surface, we will end up with a three-dimensional space because 2 dimensions are for x and y, and the third dimension is the value of f depending on x and y. And this g function, it's also the surface that this function creates is also in three-dimensional space. But actually when we say, okay, this value is 4, we only take the one contour line of the surface. And I will give you an explanation of what are contour lines, and I will try my best to visualize them. Let's look at the contour lines of this function. I will try my best to visualize it in a three-dimensional space. Let's say we have x and y, and the third dimension z is the value of our function. And let's say we have a surface like this. This is the surface that we have. I know it looks terrible, but this is the best I can do. So you can think of it as a surface in a three-dimensional space. And then what are the contour lines? Imagine that we look at this function from the top. And these, I had to draw it a little bit like this. Let me just, delete this thing from here. I will try to draw it in a better way. So if you look at this function from the top, what kind of things they form in the xy space, we will get the contour lines. And as you can see that at these points, the value of z does not change. It's constant here, 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 and here. And we try to now draw them in our two-dimensional space. So basically, we are looking at this function from the top. And what we'll get here is that these contour lines. And at these lines, the value of f is a constant. For all the points here, the value of x and y is some constant. So C1 for this line, and for this line it's C2. For this line it is C4, and etc. We can do the same for this one as well. Actually, what I drew here, it more looks like the surface and contour lines of gxy, because the surface, they're basically circles. But it doesn't matter. We can do. My point is that we draw any function, let's say, depending on x and y. And we look at the surface from the top, we will see the contour lines like this, and this is x and y. And one more important point here is that, let's say we are at this point in the function. Let's say we are at C4 at this point. In which direction should we go in order to reach the next value of our function? Should we go this way? Should we go this way? Or which way? Of course, we should go this way, because this way will be the fastest, because the distance is less. And it turns out that this direction is perpendicular to the contour line. And it doesn't matter where we are, it will be the same direction. Not the same direction, but it will be perpendicular to the contour line. If we are here and we try to go to the next point of our function, we should, the fastest way, we have to go in a direction that is perpendicular to that contour line. So we know that. And right now I will draw two surfaces. The same for, I will draw the surface for fx and y and gx and y. And I will not draw the surfaces, I will basically draw the contour lines of them together. Let's say we have let's say this is the contour lines of G. And let's say this is the contour lines of our F. So at these points, let's say F, X, Y, C1, this is F, X, Y, C2, this is F, X, Y, C3, and for the same, we take G, X, and Y. Let's say what happens here. So we know that in order for us to have a solution to this function, these points should lie on the circle. So these points should be somewhere around, let's say this is our specific contour line, the constraint, and we write it as x squared 4. So we are interested in this contour line, but I have to draw more contour lines of F to correctly visualize it. And this is our constraint, and this is our function. And you can see that geometrically the lines and the lines of the circle should touch or should intersect. This is our first thing that we have to have. Let's look at these points. Why? Because at this point x and y satisfy the constraint, and also it's a value of our function. But it cannot be optimal because, as you can see, that at this point, when we move along the circle here around this point, the value of the f changes. When we move on the circle, the constraint contour, the value of f changes. So what it means that if we look at this point and say that this is a minimal or maximal, it is not possible, because if we just go a little bit into this direction and take this point, the value of the f is bigger here than it is here, and it also satisfies the constraint. So it's not possible that the optimal points are at the intersection of our contour lines for this reason. So we have to look at the points where the contour line just barely touches our contour line of f, barely touches the contour line of our constraint. And one of those points is here, and one of those points is here. And here is the magic. As we talked before, at this point, let's first look at the direction where we have to go, and it should increase the value of g function, this function, the fastest. And which direction is it? It is perpendicular to the contour line. And the same way, when we're trying to find a point where from this point, when we move to the next point of our f, it should be the fastest. And at this point, it should be also, let's say, if we are looking for the minimal point, the minimum extremum, it will be in this direction, right? Just a second. So at this point of our f function, we're trying to calculate the gradient, which is just a vector. And this vector should give us a direction of the fastest change in our f. And we know that it's this direction. And we also calculated it in our constraint surface. It's this direction. And as you can see that they are at the same direction, or at least in this case, they are quite opposite, but if we just make alpha minus 1, we get the same result. So that's why we need alpha. Or, for example, this constraint gradient vector is maybe a little bit bigger than of our gradient vector of our f. So that's why we need to have this lambda here to account for that scaling issue. And that was basically the intuition behind why the gradient of f at the optimal point is in the same direction as g, the constraint surface. And after this step, we will try to write this in a way that is more compact and it's easier to computers to calculate.